Today we're looking at adding and subtracting radicals and multiplying radicals as well. And it's building on the work we did previously with simplifying radicals, so we'll also have steps where we are simplifying. Here, to start us off, you can see our list of perfect squares and perfect cubes, again, just for reference, as we'll be needing that information in these problems. And we have a number of basic sort of building block examples before we get to the more complete examples underneath. All right, so when we're talking about adding and subtracting radicals, we're really talking about, do we have like terms? And you're looking at both the radical itself, so these are both square roots. You're also looking at the value inside. So it's much the same as if it has a typical problem without a radical. Do you have like terms, right? So you know 1x squared plus 1x squared, you are adding the coefficients to get 2 in front of that x squared. Same idea with the radicals. You're adding 1 root x plus 1 root x, and you get 2 root x. So you're adding the coefficients in front of the radical. And you have to check to make sure, are they both square roots, and do they both have the same value inside the radical? So when you contrast this with part C, you'll recognize that they're not like terms. So they can't be simplified. All right. They would just remain in that form. Now when multiplying, we saw this a little bit yesterday, when multiplying, we will multiply under a common radical. So the square root of x times x is equal to square root of x squared. So again, notice the difference here with the addition problem. So we're not creating a common radical and adding x plus x underneath the radical. No, we're adding the coefficients. That's just counting how many radicals we have. And here we're multiplying underneath a common radical. All right, anyway, that simplifies to just x to the power of 1. Same if you have root x times root y, you can multiply those under a common radical. Here's another little mini example, root x times root x. Same story, you can multiply those under a common radical, and that would give us x cubed. Right, so we add up those powers. 1 plus 1 plus 1 gives us the power of 3. Now we saw this previously. When you have a power of 3, you want that to try and match the index of 2, so we're going to regroup those. So we have an x squared times an x to the first, so that we can simplify this x squared, giving us an example of x times root x. With the next example, cubed root of x times another one of them, again, we can multiply those under the common radical and we'll get x cubed. So here you do see the power match the index, so that simplifies right away. So these next two are odd little cases, so keep in mind if you have a negative sign how we want to address those. Here we have the square root of a negative, here we have the cubed root of a negative. Let's compare them. So with the square root of a negative 1, this is your undefined result. If you're not sure, you can type this in your calculator and it will give you the error message. So technically there is no answer, not even a 0, right? 0 at least is a measure of something. But this is undefined. It cannot be solved. So we get around that by defining it with this I. We say, let's just call it the imaginary value I. So we cannot take the square root of a negative, but can we take the cubed root of a negative? And the answer is yes, because look, you have negative numbers in your perfect cubes, including negative 1, negative 8, negative 27. So yeah, we can take a cubed root of them. And so this answer does give you a valid answer. All right. Now let's go to the real examples. We're looking at adding or subtracting, in this case, these radicals. And we're looking again to see, do we have like terms, right? We want to know, do we have the same radical and the same value inside the radical? And in number 1, we definitely have the same radical and the same number in the radical. They're both root 3. So yes, they are like terms. They do combine. So combine those coefficients. Negative 5 of the root 3 minus 3. More of the root 3 combined to a negative 8 of the root 3. Same here in number 2. I'm looking to see, do we have the same root? And we do. We both have cubed roots. They have the same value under the radical. So yeah, they are like terms. So we have 2 of the cubed roots, and then we're subtracting 1 of those cubed roots, so that means we have 1 left. So we have 1 remaining of the cubed root of -8. Now we want to see if we can simplify the radical, and it looks like -8 is a perfect cube. So yes, we can take the cubed root of -8, and that will give us a -2. How do we know it's a -2? Because it's the second number on our list. So we generated this by going -2 cubed is -8. So working backwards, the cubed root of -8 gives us -2. Here in problem number 3, our terms are not the same. We don't have like terms, so they cannot be combined. So you might think we must be done. They can't be simplified. They can't be combined because they all look different. Not really. We can manipulate them by first factoring the 12 and the 20 to see if we can find factors to change its form. So let's see what we can come up with. So factors of 12, we're talking about perfect squares here now, so we want numbers from our list of perfect squares. And we can use that factor of 4. So how about 4 times 3? The middle term will stay the same. There are no other factors of 3 that we want to work with. And then factors of 20. How about 4 times 5? And then we can take the square root of those perfect squares, the 4s. So we have this coefficient of -3 in front. We'll take the square root of 4, that gives us 2, and then we have the root 3 at the end. The middle term stays the same. The last term, we have the coefficient of 3 times the square root of 4, so that gives us a 2, and then we have a root 5 at the end. So I'm going to make my coefficients a single value, so we should have a -6 in front of that root 3. Again, the middle term stays the same. And then we have a coefficient of 6 in front of that root 5. Now you can see we do have like terms because these first 2 terms have the same radical with the same value inside. They both have root 3's. So these can be combined. The third one cannot. So we have -6 of those root 3's increased by 3 of those root 3's. That turns into a -3 root 3 plus 6 root 5. And that's the final answer. We cannot combine those because they have different values under the radical. So that was an example with a square root. Now let's do an example with a cubed root. That's what we see here in number 4. We have lots going on here. There's the negative sign in front, and then we want to find factors of 320. Now again, you probably don't know them, and I don't either, right? So this is where we use our calculator with those really big values to guess and check to figure out which of these numbers we can use as a divisor, right? So we might guess and check 320. Is it divisible by 216? It's not. And then keep working down your list until you find one that does work. And it's 64 that happens to work out. So I did that earlier, so that's the only reason why I know it's 64 times 5. All right, the middle term here, or the second term, we have -4 times the cubed root of. This is sort of the key element of this example. When we're going through this, this is really what I want you to pay attention to. What do we do if we have a negative sign under that radical? That's what this example is really focusing on. Again, when we have these numbers, these big numbers, we know there's probably some factor combination. What I want you to think about is that when you see a negative sign, that is also a factor combination because -1 is one of our perfect cubes. So always separate -1 from the positive number, in this case 5. So yes, this is a perfect cube and we will be able to simplify that much of it. In the next term we have +2 times the cubed root of 135. Again, I'm going to my calculator to guess and check to see if that's divisible by anything, and it's divisible by 27, so 27 times 5. And then lastly, we have +2 times the cubed root of 16. That's factoring into 8 times 2. And now we're ready to take the cubed root of these values. So again, we still have the negative in front. The cubed root of 64 is 4. So again, how do we know that? Because it is the 4th term. 1, 2, 3, 4. It's the 4th term in our list. That means we got this 64 by taking 4 and cubing it. So 4 cubed is 64. So when we go backwards, the cubed root of 64 is 4. And then we have this cubed root of 5 in back of that. In this second term, we still have the -4 in front. The cubed root of -1 is -1, and we have the cubed root of 5 in back of that. For the next term, we have the 2 as a coefficient. The cubed root of 27 is 3, and then the cubed root of 5 is in back of those. Lastly, we have a coefficient of 2. We take the cubed root of 8, which is 2, and then the back of that is cubed root of 2. So I'm going to now clean up my coefficients here. You might start wanting to like combine the terms, but I'm just going to take it one step at a time. So -4 times the cubed root of 5. Here in the second term, we have a +4 times cubed root of 5. Here in the third term, we have +6 cubed roots of 5. And lastly, we have 4 cubed roots of 2. Now that I have a single coefficient in front of each radical, now I'll combine like terms, and you can see that these first 3 all have identical cubed roots of 5. So they are like terms, they will combine, and they turn into 6 cubed roots of 5 plus 4 cubed roots of 2. That one does not combine because of the different value under the cubed root sign. So that's your final answer right there. So those are the examples for adding and subtracting radicals. We're going to finish off with these two, which are talking about multiplication. So in number 5, you can see we have this binomial here, and we need to take this 4 root 15 and distribute to the two terms. Right? And so when we're multiplying, we're going to multiply the integer with the integer, and then we'll multiply the radical with the radical. So 4 times -3 gives me a -12. And then root 15 times root 6 is root 90. We distribute to the second term. Now this time there's just an integer of 5. There's no radical. So we'll multiply integer to integer. So 4 times 5 gives me 20. And then root 15 times, well, there is no other radical, so it just remains root 15. Again, we want to try and find our factors to simplify wherever possible. So I'm taking that 90 and factoring that into 9 times 10. Everything else stays the same. So we have a -12 in front. The square root of 9 is 3. That is followed by the square root of 10, and then plus 20 root 15. So to finish this up, we'll just turn this front into a single coefficient. So that will be a -36 times the root 10 plus 20 times the root 15. That's our final answer. They do not combine because those radicals are different. So in number 6, we have a double distribution. We have a binomial times another binomial. So we use this FOIL acronym to help us remember the multiplication of each step. F stands for the first of each term. So you can think of that like a distribution, right? And then the O stands for the outermost pair. So you can think of that -7 as being distributed to the binomial and back. So -7 times 4 is -28, and -7 times the root 3x is a -7 root 3x. The I stands for the inside or the innermost terms. So now we're taking this 3x and we're distributing it. So the I stands for the innermost terms and the L stands for the last of each pair. So again, you can think of this root 3x as that being distributed to the binomial in the back. So with this multiplication, we have a +4 root 3x. And then with the last times the last, we have a +root 3x times another +root 3x. You might be able to do that in your head, but I'm just writing it down just to make sure that we know what we're looking at this step and how to multiply that out. These middle two terms are like terms. They both have the same radical of root 3x, so they can combine into a single term of -3 root 3x. And then to multiply these together, we can do that multiplication under a common radical. So 3 times 3 is 9, and x times x is x squared. And hey, that can be simplified because those values are a perfect square, and that turns into 3x. So we're technically done with the multiplication. However, there's a formatting issue, and that is we always want to write our terms in descending power order. So this is x to the first power. This is a square root, so that's really, you can think of that like a 1/2 power. And this has no powers of x. So that would be, you could think of it like x to the 0 power, for example. So we just need to shuffle the terms around. So we would lead off with +3x, and then the middle term is -3 times square root of 3x, and then we finish off with the constant term of minus 28.